All right, let's get started. We last time we were talking about the sign convention, and now I want to do a little consideration about the relationship between the shear diagram and the moment diagram and the loading. Basically, we have shear and moment because we have load on the beam. So let me draw here a little beam. This is a beam, and then the beam has some load. Let's say a very general load, a bunch of stuff on the beam, and there are some reactions here. At point A, we have a reaction at A and reaction at B. And because there is this loading, you will have shear and moment on the whole length of the beam. So let's analyze what happens on a little piece of the beam. If we make a cut here and analyze a little piece of the beam, let's say you cut here at a distance x from the origin here, and then we analyze that piece of beam. I'm gonna expand it here. This is a little piece of the beam. This little piece of the beam is right here, right? So you will see shear force here and moment here. And at the other side, you also will see shear and moment. Let's call this one. I don't want you to be confused. Remember, I used to do the cuts like this before. This is the cut, right? And then I have the shear here and the moment here. But if I do the cut here, I will see the shear here and the moment here. Now I am analyzing just this little piece between these two cuts. That's what I have here on this diagram. And I'm going to analyze a little piece of the beam in order to understand how the shear and the moment develops along the length of the beam. Let's call this moment M, and this will be the same moment M plus a little change in M that will occur as we move from this section on the left to this section on the right. This distance being a very short distance, let's call it delta X, right? And of course, there will be some kind of load here associated with that piece of beam here. A tiny piece of load W, or you can call it W of X. This is like a little slice of the beam. The load is not supposed to change too much from here to here because the distance is very short. It's just delta X, and we are going to make that delta X to tend to 0. So we are going to establish the kind of like the equations of how the shear and the moment develops as you move along the length. So if this is the shear V, this will be V plus delta V. What does that mean? That means that if the shear is a value here, we can expect that as we move to the right, the shear has changed a little. The change in the shear is going to be delta V, and the change in the moment is going to be delta moment. Because there is some loading, it's expected that the shear is changing and the moment is changing. The change is delta V, and the change in the moment is delta M. So now let's analyze those. So we have the summation of forces in the y direction has to be equal to 0 for this diagram here. I'm analyzing this free body diagram. For that free body diagram, summation of forces has to be equal to 0. Everything is in equilibrium. Let's do positive going up. So I have V minus V plus delta V minus the loading. The loading, remember when we were talking about distributed loads, that if I have a load that is in terms of the length, then there is like I can do like an equivalent load here that will be of magnitude W times D, right? If I have like the examples that we had in the previous class, we have like 400 newtons per meter, and we have that load apply over the length of 3 meters. That means that For every meter you have 400 newtons, so in 3 meters you have 1200 newtons, right? I hope this is already understood for you guys. So here the load for this load here is W times delta X. That will be the load. So those are the 3 loads on this free body diagram encircled in green. So this is equal to 0. And then from here we can get V minus delta V minus W delta X equals to 0. So I have here V and V goes away. So I have minus delta V minus W delta X equals to 0. So delta V equals to minus W delta X, right? If I go to delta X tending to 0, we go to the expression dV equals minus W dx. This takes me to 2 things. Oh, no, mainly one. Let me get rid of this stuff. Take me to this expression. I can integrate this on both sides, and I have that V is equals to the integral of W dx. I want to point to this expression here. That means, and it's going to be helpful to do our diagrams, that the shear diagram is the integral of the loads. An integral meaning summation. So all you are doing when you are doing a shear diagram is doing a summation of all the loads. So you start to sweep your beam from left to right, and as you are moving from left to right, you are making the summation of all the loads that you are finding on your way. And as soon as you find a load, you add it, and then you find another load, you add it, and you make a summation of it. If the load is in one direction, it's going to add. If it's in the opposite direction, it's going to subtract. But it's just a summation. Summation means algebraic summation, so the terms go with sign. That's all you do when you do a shear diagram. Make a summation of loads. That's all you do. It's gonna be very simple. You're gonna see. Now same thing for the moments. Let's do summation of moments about the right of the element here. Summation of moments equal to 0 about the right of about this point here. And let's do whatever. Let's see positive in this direction. Then what do we have? We have M minus M plus delta M plus the moment produced by V plus delta V. That will be V plus delta V multiplied by the moment, the lever arm, which is delta X. Now the moment produced by the load, that will be a concentrated load right here in the middle, right? The magnitude of that load will be W delta X, right? Minus W delta X. And the lever arm is half of the length of the element. So that will be delta X over 2. I am assuming that the load is rectangular distribution here because the piece of beam that I am analyzing is so little that the change in load is going to be neglectable. So I can consider that load like a rectangular distributed load. So I can say that the center of gravity of that little load is in the middle. That's why I do delta X over 2 for the lever arm of the force mean W delta X. If anybody sees any other load, tell me what any other force on this summation of moments? Any other force? Moment. The other moment. The force. No, this is a mistake. This doesn't work because this force goes through the point that I am making. So what I have to do here is V times delta X. I have to get rid of this. This is not right. This doesn't produce moment. This one produces moment. Well, V times delta X. And then this is equal to 0. So I have M minus delta M plus V delta X minus W delta X squared over 2 equals to 0. The term delta X squared, when I go delta X tends to 0, disappears because it's a term of the second order. So I will have M goes with M, and I have minus delta M plus V delta X, and this one goes away, tends to 0, equals to 0. So I have delta M equals to V delta X. So I have two expressions here. When I go delta X tends to 0, I have Vm equals V delta X. So I have two things here. I can do this as V equals Vm dx, or I can take integral on both sides and say M equals integral of V dx. This is the result that I wanted to get here, which is going to help us do the diagrams. In one aspect, V is the slope of the moment diagram. The shear diagram shows the slope of the moment diagram. And the moment diagram is the integral of the shear diagram. So the same way like the shear diagram is the integral of the loading, the moment diagram is the integral of the shear. So we could use the same techniques that we used to find the shear diagram based on the loading. We can use the same technique to find the moment diagram based on the shear. See, the expression is very similar. Keep that in mind. Remember, the moment diagram is the areas. Integral means areas, right? Integral means area. Integral means area. When you do an integral, you are doing area. The thing is, sometimes in the loading, many times you have a concentrated load that doesn't look much more like an area, but we will see how we treat those. And sometimes when you have a concentrated moment, it doesn't show like an area, but like a concentrated jump in the diagram. We will see how to deal with that. So let's make an example in order to apply these concepts, but keep that in your head. This is the most important here. The shear diagram is areas of the moment diagram is areas of the shear diagram, and the shear diagram is areas of the load, but I like it better to say that when you do a shear diagram, you are doing just a summation of loadings. All right, let's go to the example. Let's do this example. I have a little beam with one load of 21 pounds at 2 feet from the left, 4 feet from the right. We need to calculate the reactions first. Before you start a shear and moment diagram, you have to have all the loads on the beam. Means you need to find the reactions. At this point, you have to be very good at finding reactions, right? I don't know if it's necessary to go over this, but let's do it one last time. From this time on, you guys can find your own reactions. Let's do summation of moments at point B equals to 0. I'm gonna say positive in this direction. Then I have RA times 6, RA times 6 minus 21 times 4 equals to 0. Somebody can tell me what is RA equals to 21 times 4 divided by 6. Somebody can tell me what is this?
14.
14. Look, I got 14 too. Great, thank you. To confirm that this is correct. It's good to have at least two answers. And then I do summation of moments about point A equals to 0, and we are going to do positive in this direction. So we have RB times 6 minus 21 times 2 equals to 0. So RB equals to 21 times 2 divided by 6, 7. You got 7? I hope you guys got 7. So if you allow me, I'm going to erase the supports here on the left in order to type the reactions, to plot the reactions. So I have here a reaction of array is 14, and this one is 7 pounds, and we are ready. We are ready to start. Okay. So the way I do the shear diagrams is like this. Pay good attention to this. You won't see this anywhere else. This is your shear diagram. You are going to be adding forces as you move from left to right. So as soon as you get you find a force, you add it or subtract it, depending if it's going up or going down. So you come like this. This is the shear diagram. In the air there is no shear. So you come here at 0 and you go like this. You have to make that noise when you do a shear diagram. Soon, here you find a force, 14 going up. So you do whatever the force tells you to do. You move 14 up. So you need to establish a scale here. 5, 10, 15, 5, 10, 15. So at 14, you stop at 14. Here at 14. Then on this region, you don't see any load, so you keep moving horizontal because you don't move. There is no force telling you anything, so you keep going. Boom! You find a force of 21, so then you go down 21. What is 14 minus 21? Minus 7. Minus 7. So I have to put my scale here, minus 5. Minus 10. So in minus 7, you stop. Minus 7. And you keep going. Boom, another load is telling you go up 7. So you go up 7. And then you keep going. And you have to make sure that you end up at V equals 0. Because you have to start at 0 and finish at 0. So this is minus 7. And this is plus 14. That's how you do the shear diagram. You just start on the left at 0, start moving to the right, and as soon as you find a load, you do whatever the load is telling you to do. And the load is showing you how to move because it's an arrow. If the arrow is pointing up and it says 14, it's telling you move up 14. If the arrow is going down and it tells you 21, you have to move down the 21 pounds that the arrow is telling you to do. Easy. That's how you do a shear diagram. What was the scary thing about shear diagrams? Easy? Difficult? Questions? No more questions.
Professor, can you show us again the equations you did for this to find 14 and 7?
Oh, that was the calculation of support reactions here. So that's just how you calculate the reactions. So you take summation of moments about point B. That's it. And then you get that reaction at 8 is 14. And then summation of moments about point A here is just RB times 6 minus 21 times 2. And then you get RB equals to 7, right?
Okay, thank you. I just needed to check.
Just reactions.
Can you go over the diagram after you get to 14, please?
Okay, let's go back to the diagram. The way to do the diagram is that you just, let me repeat this. You just start moving. I remember there was a computer language, a programming computer language for little kids that used to be a long time ago. I don't know if you guys saw it. The little kids have to give commands to a little turtle that was drawing on a board, and the turtle have to do the commands that the kid give the turtle, and the turtle was moving, and the kid was telling the turtle, move up 14, and the turtle started moving up. And then move horizontal, move down 21, move down 21, move horizontal, then move down 7. And then the turtle was just doing whatever the kid was telling the turtle to do. So that's exactly what you have to do. Imagine that you are a little turtle moving from left to right and obeying the commands of the loads. You have 3 commands here. One command is go up 14, another command is go down 21, and another command is go up 7. So that's exactly what you do here. I'm gonna do it here really quickly again. So I start here at 0, and I go chuku, 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 chuku. As soon as I found the load that says go up 14, I go up 14. So I reach the 14 level here. I keep going horizontal because there is no loads in this region. There is no load, so I don't do nothing. Then I found here the load of 21, so I go down 21. If I was at 14, I have to go down 21, so I reach to -7, right? So 14 minus 21 is -7. Then I keep going horizontal because there is no loads in this zone here. And then I found the load of 7 going up, so I move 7 going up. I was at -7. If I go up 7, I end up at 0. And then I end up at 0. That's how you do the Shear diagram. Very easy. Very easy. I want to see 22 answers. Say easy, very easy. Ah, yeah, easy. Anybody else? Or somebody else say, no, difficult, difficult. Not bad. Great. Easy, perfect, easy, easy, very easy. All right. It's gonna get a little bit more complicated when we have distributed loads, but it's not much complicated. It's kind of the same. Fácil, fácil, Emily. Muy bien. Let's go to the moment diagram. Moment diagram. Moment diagram. Let me, the moment diagram, remember, the moment diagram is the area of the shear diagram. That means that I'm gonna have a diagram here. Every point on this diagram is gonna show me the total area up to that point from the shear diagram. So let's do. We start at 0. We always start at 0. And then at this point, for example, at this point, I'm gonna have a point over here that is all the area on the shear diagram from 0 up to that point. In this case, that area will be the area of this rectangle here. That will be the area. It will be equals to 14 times 2, so it will be 28. So this point here is 28. So let's put an scale here. So this will be 10, 20, 30. So this will be 28 here. 28. So I am a little bit up. So I'm gonna have a straight line that reach here the point of 28, the area of this diagram here. Okay. Now, why is a straight line? Because remember the other thing that I said is that the shear diagram is the slope of the moment diagram. The shear diagram is telling me that the slope is 14 all the time. 14 all the time means that the slope of the moment diagram is constant. So it means it's a straight line with a certain inclination, a certain slope. Constant at 14 all the time. So it's a straight line. A straight line has the same slope at every point. So that's why this is a straight line. Now the shear diagram is telling me that the moment diagram has a slope of -7. So I'm going to have a line that is with negative slope like that, right? But up to what point I'm going, if I want to find the moment, shall it get here, shall it get here, shall it get here? Well, the way to find the exact point where I should take my moment diagram is to find this area. So here at this point I have at 28. Now if I at this area, I will get to the final point at the end of the beam. This area is equal to -7 times 4, right? 4 feet. This is -7 pounds times 4 feet. So this is -28. So I was here at +28. If I subtract 28, I'm gonna get back to 0 here. And it's gonna be a straight line because the shear diagram has constant value along all this distance here, all this length here has -7. So the slope of this line is -7. If you want to calculate the slope of a line, how do? You get the total height over the total horizontal here, the height over horizontal, so the slope is A over D. In this case will be 28 divided by 4. So this is, and it's 28 negative because it's going down. So it's -7. See, this -7 is less the slope of this line, which is what the shear diagram is showing as the value of the shear on all that length. Okay? Clear? Question? Questions? Questions? Easy? Then we have our moment diagram just like that. Easy? Complicated? Difficult? Lemon difficult? What does it mean, lemon difficult? Does it mean difficult? Or so is the slope of the first line? The shear diagram, this 14 is the slope of this line. This 7 is the slope of this line here. I don't know if I'm. This 14 is the slope of this line. This 7 is the slope of this line. Okay? Okay, let's do another example a little more elaborated than this one, okay? Another example here. You guys should be able to find the reactions of this beam. Okay, I'm gonna give you guys a little hint. In order to get the reactions on the beam, you do the same thing. You say here reaction A, reaction B, and you do summation of moments about point B equals to 0, positive in any direction you want. I like this. So I do RA times this distance, 24, minus 20 kips times this distance, 18, minus 20 kips, 12 kips times 10 feet, plus, now this load, you have to replace this load by an equivalent concentrated load that will be here in the middle. And the value of that load will be if you have 1.5 kips per foot and you have it for 8 foot, so then you have 12 kip, or being 1.5 per every foot. If you have 8, then you have 12, right? And you put it in the middle because it's a uniformly distributed load. So this distance will be 4 feet. So this will be 12 times 4 feet equals to 0. Okay? And that's how you get RA. And same thing for RB. You do summation of moments about the point A equals to 0. You do positive in this direction. You do RB times 24. All right, minus 20 kips times. So the distance from the 20 pound to the point 8 is just 6. The distance from 12 kips to point 8 is 8 plus 6, 14. And then you have this force that produces moment positive, so plus 12 kips times the whole distance from this force to this point here. That will be 24 plus 4. This is 6 plus 8. plus 10 plus 8 over 2 equals to 0. That's how you get RB, okay? Summation of moments about point A, summation of moments about point E, and you have to calculate all the moments from all the forces. Clear? Got it?
Question: once you get RA, can't you just do like all the negatives and all the positives? Like, cause can you
Yes,
do that too?
yes.
Yeah. Okay.
Yes. Here you got RA equals to, let me put it here. If somebody does that operation, you can do it. RA equals to 18 tips, and RB equals to, no, it's 26. Actually, it's not D, it's D, actually, it's D. Is the point D. But the thing is, I like to do summation of moments instead of summation of forces, because if you made a mistake when you calculate the 18, you're going to make a mistake also in the other reaction if you use this one to calculate the other. In this case, they are independent. And then what you do is you do a summation of forces in the y direction to check if everything is correct. Let's check. You have 28 going up plus 26 going up minus 20 going down, minus 12 going down, minus 12 going down, right? So this is 20, 30, 40, 44, and this is 24 equals to 0. So, okay, you use the summation of forces in the y direction to check if you did good job calculating the other two.
Yeah.
All right. I always calculate reactions that way in order to make sure that if I make a mistake in one of them, I don't make mistake in both. Shear diagram. Okay, listen to this. Listen to this and look at the diagram. I go here, chuku, 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 boom. I get a load, 18, and the arrow is showing going up, so I move up 18. So I better make some scale here. 5, 10, 15, 20. This is 20, this is 10. So 18 will be like over here. So then I have to go up all the way to 18. Then I move to the right, no forces, so I don't move up, I don't move down. Chuku, 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 chuku. Boom, 20 going down. If I was an 18 and I have to move 20 down, what do I get? Minus 2. So I have to do my scale here. 5, 10, 15, 5, minus 5, minus 10, minus 15. So I get here to minus 15, minus 2. And minus 2, I keep going horizontal. Boom. So I was here at minus 2. Now I find minus 12. So I have to keep going down minus 12 additional up to minus 14, which is over here. So up to here. Minus 14. No more forces. Then horizontal, right? And then boom, plus 26. So I go from minus 14 plus 26. That's 12. So I go 26 going up 26 up to 12. 12 is like over here. So that will be over here. Boom, 12 plus 12. And then what happens here? I cannot keep going horizontal because I have load that is telling me go down. So I cannot keep go horizontal. I have to go down. But I'm not gonna go down on a vertical line because the law is telling me to go down, but smoothly down, gradually down, at a rate of 1.5 kips per foot. So if I have 8 feet here, this is 1, 2, 3, 4, 5, 6, 7, 8. So per 1 foot that I move here, I have to move down 1.5. So I will have to go 1.5, 1.5, 1.5, 1.5, 1.5, 1.5. For every foot I move down 1.5. The slope of this line, the slope of this line is this value here, 1.5, same thing. But that concept of the slope here maybe makes the things more confusing. I don't like to do that, but that's what it is. It's just that you go down at a rate that you move down 1.5 for every feet that you move horizontally. So you go down like this. 1.5 keeps going down as you move to the right one foot. And the rate is constant, so the line is a straight line. It would be a straight line like this. Make sense? Is it clear? Questions? No questions?
This seems good. It's easy.
Easy, easy. It's easy. It's done. That's the shear diagram. Let's do the moment diagram. It's gonna be a little bit more complicated because of that inclined line over there, but not terrible. So we can hide the diagram up there because we only need the shear diagram in order to do the moment diagram. Moment diagram. Let's see. We said the moment diagram is the area of the shear diagram, and the shear diagram is the slope of the moment diagram. If this 18 is a constant value for this first segment here, it means that this moment in this region is a line with a slope of 18 and constant slope. So it's going to be a line like this. So from 0 to some point here, what is the value of this point up here? Is the area on the shear diagram up to that point. So what is that area? That will be area from A to B. Area from A to B is equal to 18 times 6. 6 por 8, 48. 6 por 1, 108. 108. Perfect. So this point here is gonna be let me put some scales. So I have to go up to 108. This is 100. This is 50, 50, 100. So this is 10, 20, 30, 40. So this is kind of 108. So it's gonna be this line. So that's the moment diagram from A to B. You see that it's a straight line with constant slope of 18. If you want to look at the slope, it's this, which is 108, divided by this, which is 6. What is 108 divided by 6? 18, right? Which is this value here on the shear, right? You see how the slope is the shear, the slope of the moment is the shear. I want you guys to be aware of that concept right there. Let's continue. Now we are here at 108. Now we have some area, negative area here. This area here is A, B, C equals to minus 2 times 8 minus 16. That means that from 108, I have to go down 16. 108 minus 16 is 92. So I should get here up to a point of, this is 90, 92 will be like over here, something like this. It goes down to a point with a coordinate of 92. Now I have to go down all the way over here. I don't know exactly where, so some point over here. and also constant slope of minus 14. So it's gonna be something like this. To do it, I would like to find out what is the coordinate of this point down here, which will be 92 minus the area between points C and D. What is the area of this area C and D? This area here. That
120.
area CD will be minus 14 times 10. 140?
Shouldn't you go from 2 though, because you're starting at -2, or is it the from B?
Is the area of this figure here, right? Is the area under the shear diagram. The area under the shear diagram is all the way from this value to the value here. Make sense?
Yes.
Yeah, there is no point on subtracting this minus 2. This minus 2 is for this area here. And this minus 14 is all this area here. Okay? Yeah, that tends to be something that confuses you guys. In the other classroom, they made exactly the same question. No, the diagram, the moment diagram at any given point is the total area under the shear diagram. And the total area is measured from the axis to wherever the graph is. So it's all this area, from the axis to wherever the function is located. So here we get 92 minus 140.
Negative 48.
Negative 48. Negative 48, yes. So if I have my scale here, this is 50, so this is 50 minus 50, 48 will be something over here. Okay, so it will be over here. So we will have a straight line like this. And here we get minus 48. Now the last piece. Now we have to get to this point here by adding this area. This area is equal to 1/2 of 12 times 8. So 48. 48. So look, we have 48 here plus 48. This has to go down to 0, but not a straight line. Not a straight line. Maybe like this, maybe like that. Why not a straight line? Because the shear diagram right here is not constant slope. If this was constant slope, it will go straight down here. But it's not constant slope. The slope is decreasing, and the slope is 0 at the end and some value at the beginning. Actually 12 at the beginning. So we know that we have to end up at 0, and we have to end up with a 0 slope. 0 slope. What does it mean, 0 slope? 0 slope means horizontal. So at the end, this line has to be horizontal. And at the beginning here, it has to have a slope of 12. So it's a high slope here. And the slope is reducing little by little as we go down to 0 slope. You see, as we go down, the slope that started at 12 decrease until it gets to 0. So this slope here starts at some value and decrease until it gets to 0. It's something like this, with a slope of 12 and a slope of 0. The slope we usually say m, right? M equals to 0. This is the graph of this portion of the diagram. Let me get rid of this stuff here. So I have a lot of slope at the beginning, and less, and then 0 at the end. It's not bad, but a little bit high.
Professor, I don't understand how to determine when the curve goes like one way or the other? Like if it curves up or if it curves down?
Right. This, I'm gonna put it right here. So I have, this is that part of the graph, ¿cierto? Start at -48 and at 0, and the slope here, what means the tangent of the curve, this slope is whatever value the shear diagram has. In this case is 12 up here. You see the 12 right here, 12. So this slope is 12. That doesn't tell you too much in order to draw the line, but it's just meaning that it has positive slope. Positive slope. That's all you care to draw the diagram. Positive slope. So it's a line that's going up, not going down. It's going up, not down. Up, up. So you know how the line starts, and then the slope is decreasing because this 12 is becoming 12, 10, 8, 4, 5, 0. At the end, the slope is 0. So at the end, you know that is an horizontal line. So you have to connect these two slopes, the initial and the end, with a line. So you will do something like this. The slope is decreasing. You see the slope is the tangent. The slope is decreasing until you get a slope 0. That's how you get this graph. All right?
Thank you. I get it.
All right. Okay. Now, if you want, you could, but it's a little too much work, but you could find a point right in the middle. You can find a point right in the middle. If the point is here, then you do this graph like that. But you have to, something that really helps is to know that the slope, how the slope changes, that's how you draw this line. But if you put a point in the middle by drawing a line here at the middle, here at 4 feet, and then you calculate the area up to that point. If you calculate the area up to that point, this is a trapezoidal thing. That's what I'm telling you. It's a little bit annoying because then you will have this graph like this. You will have 12 here. This is supposed to be a straight line. In the middle will be 6. In the middle, this will be 4, and this will be 4. So what is the area of this? The total area of that triangle was 48, right? Or you can calculate this area, which is kind of easy. It's 1/2 of 6 times 4, so it will be 12. So this area is 12. So you know that this value is 12, right? If you go like this in the middle, this is the half of 48, so this is 24. So now you know that in the middle, in the right middle is 24, but it should be 12, so you know that the graph goes like this, right? And you know that at the end has to be horizontal, so something like this. At the end has to be horizontal because the value of the shear diagram is 0 here. So the slope at the end has to be 0, horizontal. A slope of 0 means horizontal line. Okay?
So, quick question.
Yes.
So let's say it was going instead of from 12 to 0 in the shear diagram, it was going from 0 to 12. Then the curve would be from the same point, but it would be just the other way. It would be like starting with a slope of 0 and then curving into a slope of 12, right?
Right. But it's not gonna work in this diagram because it will not match at 0. But
oh no, I'm just making a hypothetical situation that's going to be somewhere else in the graph. Like if you're going from 0 to 12, then it would be the other way. The curve.
Let's suppose that you have here 0 to 12, something like that, right?
Yeah.
And then suppose we were in this point here, the same point, and then I have here 0 slope, and then going up to some vertical slope. This slope will be 12, right?
Yes.
Oh, I screwed up all this stuff. This will be 12, 1. Yeah, from 0 to 12. You really don't look at the actual value of the slope because that's very difficult to do when you are drawing a line. You really don't know what is the slope of the line that you are drawing. But what you really look at is if the slope is positive or negative, and if the slope is decreasing or increasing. That's all you do check in order to do your drawing. 0 is you just 0 you use it because 0 means the line is horizontal. So from that information, you drew your lines. Let's say this is a shear diagram. This is a moment diagram. Let's say you have this. Let's say you have this, and in the moment diagram, you have something like this. You start here. The slope is negative. Let's say this is the axis. The slope is negative, so you start like this. Negative slope. The slope is 0 here. So here at some point, the line has to be horizontal. And then you have positive slope here. So here it has to be like that. So you will have something like this. See, 0 slope here because the shear is 0 here. Negative slope here, see, going down. Positive slope here, going up. See?
Mhm.
Make sense?
Thank you.
All right.